Appformer is a novel mobile application prediction framework that integrates multimodal data fusion and data mining techniques while maintaining user privacy. The framework consists of two primary components: a multimodal data progressive fusion module and a sophisticated feature extraction module. The multimodal data progressive fusion module combines encoded data from diverse sources using cross-modal fusion technology, which synergistically fuses data from multiple modalities, including points of interest associated with base stations. These points are optimized through comprehensive comparative experiments to identify the most effective clustering method, ensuring that the inputs are refined and integrated seamlessly into the initial phases of cross-modal data fusion. In the fusion process, temporal units are encoded via word embeddings and merged in later stages, facilitating efficient data integration. The feature extraction module employs a transformer-like architecture, specializing in time series analysis to extract comprehensive features from the fused data. The module's encoder-decoder architecture is optimized for multimodal feature extraction, with adjustments made to the encoder and decoder inputs to enhance the framework's performance. Appformer addresses three pivotal challenges in mobile app prediction: accurately representing core data, efficiently integrating multimodal data, and enhancing feature extraction. By leveraging attention mechanisms and transformer architectures, the framework provides innovative solutions to these challenges. Notably, the authors demonstrate that Appformer achieves state-of-the-art metrics in mobile app usage prediction, representing a significant progression in this field. The synergistic combination of the multimodal data progressive fusion module and the feature extraction module enables Appformer to deliver accurate and efficient application predictions, highlighting the framework's potential to enhance mobile app development and optimization. By providing a robust and scalable solution for mobile app prediction, Appformer contributes to the advancement of this research area, with potential implications for various applications in the mobile ecosystem. The Appformer framework integrates a cross-modal data fusion module, which combines cross-modal and self-attention techniques to fuse data from various sources, including application sequences, points of interest, POI, user IDs, and time. This fusion process ensures data integrity, fosters data synthesis, and enhances feature extraction and analysis quality. To optimize preprocessing, location and time data are refined, prioritizing user privacy and applying clustering to represent location data accurately. Time data undergoes word embedding and concatenation before fusion, ensuring comprehensive integration. Appformer's state-of-the-art performance is validated through extensive experiments, achieving scores of 31.92% and 42.68%, representing improvements of 4.75% and 7.89% over existing methods. The application prediction problem is decomposed into three components: mining and expression of core data, fusion of multimodal data, and feature extraction network. Correlation analysis reveals strong connections between time, user, and location information, as well as application usage, supporting the significance of spatio-temporal information, user information, and application usage correlations. Core data mining and expression involve data encoding, similar to word embedding in natural language processing. Word embedding methods, such as word2vec, glove, and fast text, can be applied to construct data processing methods for relevant data in app prediction. Multimodal data fusion is essential in application prediction, capturing correspondence between different contextual information data. Traditional fusion methods include co-training, co-regularization, marginal consistency, and multiple kernel learning. Recent research has introduced more complex techniques, such as deep Boltzmann machines, extensions of classical autoencoders, and nonlinear extensions of canonical correlation analysis. The Appformer framework's fusion module is built on cross-modal and self-attention techniques, ensuring seamless integration of data from various sources. Optimized preprocessing, extensive experiments, and decomposition of the application prediction problem demonstrate the framework's effectiveness in predicting mobile application usage. Predicting future app usage based on historical data is a complex problem that existing methods struggle to address. These methods are limited by inadequate data representation, insufficient data fusion strategies, and limited feature extraction capabilities. To overcome these limitations, a new predictive model is proposed, leveraging a comprehensive dataset collected from Shanghai, China, during a week-long period in April 2016. This dataset comprises anonymous user IDs, timestamps, base station IDs, and app IDs, organized chronologically by timestamp. The proposed model aims to predict the next application a user is likely to use by ranking potential next apps in descending order of likelihood. It incorporates a multi-dimensional feature sequence that captures essential historical data, including sequences of app IDs, user IDs, timestamps, base station IDs, and points of interest (POI) vectors. This integrated approach enables the model to accurately predict future app usage, enhancing user experience and improving the efficiency of mobile networks. The authors emphasize the importance of developing a predictive model that can accurately forecast future app usage, as this can significantly impact user experience and network efficiency. By addressing the shortcomings of existing methods, the proposed model has the potential to provide more accurate predictions and better user experiences. Pre-processing data for app usage prediction is crucial, particularly when utilizing techniques such as word embeddings and clustering on points of interest (POI) data. The Appformer framework, consisting of two primary components, addresses this need: the multi-modal data progressive fusion module and the feature extraction module. This pre-processing commences by converting the discrete app sequence into a continuous vector space through word embedding. This involves initializing an embedding matrix of size, n, d, where n denotes the total number of apps, and d is the embedding vector's dimension. Each app sequence finds its corresponding embedding vector using its ID, drawn from this embedding matrix. The integration of POI data is instrumental in predicting app usage patterns, as it captures socioeconomic activities reflective of base station surroundings, categorized under medical care, hotels, and business affairs, as listed in Table 2, related to Table I. Applying clustering techniques to POI data enables enhanced insights into the services available near the base stations, underpinning local functionalities and facilitating predictive accuracy in app usage patterns. Similarly, temporal data encoding enhances this capability within the Appformer framework, offering comprehensive pre-processed datasets essential for accurately forecasting app usage trends. Key insights, outlined in methodologies employed for data selection and pre-processing, involve strategically incorporating the categorized POI data alongside temporally encoded sequences. In the context of data processing, a crucial aspect is the transformation of various data types into vectors. This study focuses on the processing of application sequences, user IDs, points of interest (POI), and time data. Application sequences are embedded into a learnable parameter matrix, updated during model training, resulting in a d-dimensional vector that captures similarities and differences between apps, as well as their contextual information within the sequence. User IDs are processed similarly, using word embedding to obtain a vector representation. POI are clustered using various algorithms, including k-means, mini-batch k-means, k-means++, k-modes, and k-harmonic means. The k-modes algorithm is found to achieve the best results, involving the initialization of modes, calculation of mode distance, and update of modes through an iterative process. The POI vectors are replaced with the vector of their corresponding cluster center, obtained through this process. Time data is extracted, and each feature is subjected to word embedding, resulting in vectors that are concatenated and further transformed using a linear layer to obtain the time information matrix. The processed data is then used for further operations, including the concatenation of the application sequence vector, user ID vector, POI vector, and time information matrix, as illustrated in Figure 2. The Appformer framework is a novel approach to predict app usage sequences by leveraging multimodal data. It comprises two core components: the multimodal data progressive fusion module and the feature extraction module. The multimodal data progressive fusion module integrates encoded app vectors, user vectors, POI vectors, and time vectors step by step, preparing the data for the feature extraction module. This module's key component, the cross-modal data fusion module, is inspired by the transformers decoder module, proposed by Vaswani et al. It integrates operations such as multi-head cross-modal attention, masked multi-head self-attention, residual connection, and layer normalization, and feed-forward. In the encoder, the user vector is concatenated with the app vector and undergoes simple fusion through a linear transformation. The fused vector is then used as the query, with the POI vector as both key and value, to perform cross-modal fusion, incorporating location information. This fused vector undergoes another round of cross-modal fusion with the time vector, incorporating temporal details. The resulting vector is used as the input for the encoder of the feature extraction module. In the decoder, the app vector is designated as the query, and the POI vector as both key and value, conducting cross-modal fusion. The fused vector is then concatenated with a zero vector, used for storing predicted values, and undergoes linear transformation and positional encoding, making it the input for the decoder of the feature extraction module. Appformer addresses the limitations of existing data fusion methods by emphasizing context relevance, delineating the importance of data modalities, adopting cross-modal attention mechanisms, and implementing progressive fusion strategies. By progressively fusing multimodal data, Appformer navigates the challenges of integrating diverse data sources effectively, enabling accurate predictions of app usage sequences. The Appformer algorithm is a novel approach that integrates two key modules: a multimodal data progressive fusion module and a feature extraction module. The fusion module combines app, user, POI, and time vectors through a series of linear transformations and cross-modal data fusion operations. This results in a fused vector that is then fed into the feature extraction module. The feature extraction module employs a self-attention mechanism and a feed-forward network to extract features from the fused vector. It utilizes an encoder-decoder architecture, where the encoder processes the input vector and the decoder generates the final output vector. This module is designed to overcome the limitations of existing methods, such as NAP, Deep App, PAULCI, App Usage 2vec, and DUGN, which failed to capture subtle relationships within the data and adapt to new data types or evolving tasks. Inspired by the transformer architecture, the feature extraction module adopts an encoder-decoder architecture. The encoder transforms the fused multimodal data into a continuous representation, while the decoder generates the final output vector. This design aims to tackle the challenges of maintaining the richness of information in complex data environments and adapting to new data types or evolving tasks. The existing feature extraction methods for multimodal app usage prediction, including LSTMs, Deep App, PAULCI, App Usage 2vec, and DUGN, are limited in their ability to handle sequential data, multimodal interactions, and complex temporal dependencies. To address these limitations, a novel approach is proposed, leveraging cross-modal attention and cross-modal data fusion. The proposed model employs a combination of multi-head self-attention and feed-forward networks to capture intricate dependencies within the data. It consists of an encoder, which transforms input data into a high-dimensional representation, and a decoder, which decodes this representation and combines it with a conditional vector to produce the target sequence. The interaction between the encoder and decoder is facilitated through the cross-modal data fusion module. The encoder requires the complete dataset to generate a comprehensive representation, whereas the decoder uses this representation along with a conditional vector to make predictions. This differentiation between encoder and decoder inputs is crucial for effective prediction. The cross-modal data fusion module takes the vector from the last dimension of the decoder's output, applies a linear transformation, and uses it as the final output. The proposed approach aims to address the shortcomings of existing methods by effectively capturing user patterns and interactions across multiple modalities. By leveraging cross-modal attention and data fusion, the model can better handle complex temporal dependencies and multimodal interactions, leading to improved prediction accuracy. The novel architecture and methodology presented in this paper provide a promising direction for future research in multimodal app usage prediction. The cross-modal data fusion module algorithm fuses encoded app vector, A, and POI vector, L, through a series of operations. Initialization begins with weight matrices for multi-head self-attention and cross-modal attention. Subsequently, masked multi-head self-attention is applied to input, A, followed by multi-head cross-modal attention, where self-attention output A serves as query Q, and L functions as key K and value V. The cross-modal output is then fed into a feed-forward network, with the final output obtained after a residual connection and layer normalization. This approach yields a richer, more comprehensive feature vector, attributed to the modular design of the feature extraction module. This design allows for effortless swapping of components with those from other well-known architectures, such as Autoformer, FedFormer, and Quadformer, as demonstrated through experiments. The efficacy of different methods is assessed using evaluation metrics, including the F1 score with a macro setting. The cross-modal data fusion module plays a pivotal role in enhancing the feature extraction process, as it facilitates the fusion of multimodal data and generates a more informative representation. The authors of the research paper compare their proposed framework with various baseline methods, including traditional machine learning classifiers such as random forest, logistic regression, and XGBoost, as well as deep learning models like MLP, LSTM, GRU, PCA and LSTM, NAP, App Usage 2vec, Deep App, POL-CI, and DUGN. For the experimental setup, they set parameters for the proposed model, including a sequence length of 4, based on existing literature, and embedding dimensions of 16 for user sequences, 64 for app sequences, and 12 for time units. The framework configuration includes a model dimension of 128, 8 attention heads, a dropout rate of 0.05, and a feedforward network dimension of 512. The training regimen involves 20 epochs, a batch size of 128, and an atom optimizer with a learning rate of 0.001. The dataset cleaning and partitioning methods are discussed, with two approaches adopted from PAULCI and DUGN. The authors choose to use the PAULCI method for subsequent ablation studies and comparative analyses, which involves aggregating records where the same user stayed at the same base station and continuously used the same application for a period exceeding 1 minute, and then partitioning the data into training, validation, and test sets based on chronological order. A comprehensive comparison of the proposed method with existing methods in mobile app prediction reveals superior performance across various metrics, as summarized in Table V. Notably, the author's method outperforms others in terms of MRR and F1 scores. Ablation studies demonstrate that each component of the model contributes positively to its overall effectiveness, emphasizing the importance of a multifaceted approach. Further analysis compares the author's improved time encoding and fusion methods to a basic time encoding and addition method, showcasing the enhanced performance of the proposed approach. Specifically, the author's method achieves better results by effectively capturing complex patterns in user behavior and app usage. An ablation experiment on the input to the decoder in the Appformer model further highlights the significance of the decoder's input in achieving optimal results. The study underscores the crucial role of user information, spatiotemporal information, and historical app sequences in mobile app prediction. Moreover, the continuous advancements in feature extraction techniques have led to improved performance metrics over time, underscoring the need for ongoing research in this area. The results presented in this study provide valuable insights into the development of accurate mobile app prediction models, with implications for various stakeholders, including app developers, advertisers, and users. The experimental results demonstrate the effectiveness of the proposed Appformer model in capturing complex patterns in point-of-interest (POI) data. A comprehensive evaluation was conducted to compare the performance of Appformer with state-of-the-art methods, including MRU, MFU, BPRMF, GRU4rec, App Usage 2vec, SRGNN, and DUGN, on the DUGN dataset. The results, presented in Table V, show that Appformer outperforms all other methods in terms of MRR and F1 metrics. A module ablation experiment was conducted to evaluate the contribution of each component in the Appformer model. The results, presented in Table 7, indicate that the combination of all components, Appformer plus K plus T, achieves the best performance. This suggests that the integration of the proposed time encoding method, T, and the knowledge-aware module, K, is crucial for optimal performance. The performance of different time encoding methods was also evaluated, with the results presented in Table 8. The proposed time encoding method, T, outperforms the baseline method, T1. Furthermore, an ablation experiment on the Appformer decoder input was conducted, with the results presented in Table X. The results indicate that the optimal performance is achieved when only POI data is input into the decoder. A comparison of the performance of different feature extraction modules, including autoformer, fedformer, and quadformer, was also conducted. The results, presented in Table X, show that the proposed Appformer model outperforms all other methods. This suggests that the feature extraction modules from other models may not be well suited for the short sequence prediction task. A clustering experiment was conducted to evaluate the impact of different cluster sizes on the performance of the Appformer model. The results, presented in Table 11, indicate that the optimal performance is achieved when the number of centers is set to 5. This achieves the best performance in terms of MRR and F1 metrics. Overall, the experimental results demonstrate the effectiveness of the proposed Appformer model in capturing complex patterns in POI data and achieving state-of-the-art performance on the DUGN dataset. However, the results also highlight the limitations of feature extraction modules from other models and the importance of selecting the optimal number of centers for clustering. The evaluation of clustering methods for point of interest (POI) data requires a two-stage approach, determining the optimal number of cluster centers and assessing the performance of various clustering algorithms with this established number. This process is crucial for effective clustering of POI data, which informs the selection of suitable cluster quantities and methods. To determine the number of cluster centers, the basic k-means algorithm was employed in conjunction with Appformer, given that other clustering algorithms are often derived or improved from k-means. This choice allows for a fundamental comparison of cluster centers. Performance trends with varying cluster sizes are presented in Figure 5, which illustrates the impact of different cluster sizes on clustering performance. A more detailed examination of cluster sizes 010 is provided in Figure 6, offering insights into the performance fluctuations within this range. Figures 711 provide visualizations of different clustering algorithms, including k-modes, mini-batch k-means, k-means, k-means++, and k-harmonic means. These visualizations facilitate a comparative analysis of the clustering methods, enabling the identification of the most suitable approach for POI data. The evaluation process reveals minor differences in performance indicators among the methods, underscoring the importance of this phase in selecting the optimal clustering approach. By systematically exploring the underlying patterns in POI data, this methodical evaluation reinforces the value of a thorough investigation in understanding the data's inherent structure. The use of Appformer in combination with k-means for cluster center comparison allows for a comprehensive assessment of the clustering methods. This approach enables the identification of the most effective clustering algorithm for POI data, which is essential for downstream applications. The results presented in this section demonstrate the significance of determining the optimal number of cluster centers and evaluating the performance of various clustering algorithms. This two-stage approach is crucial for effective clustering of POI data and informs the selection of suitable cluster quantities and methods. The optimal number of clusters for POI data is 5, as determined by mean reciprocal rank, MRR, and F1 score. While the relationship between cluster number and performance is not linear, the experimental results show that performance generally declines as the number of clusters increases from 5 to 55, with some fluctuations. The correlation between cluster number and performance is weak, but 5 clusters serve as a balancing point, allowing for meaningful grouping of similar items while avoiding excessive fragmentation. The initial performance improvement from 0 to 5 clusters demonstrates the benefits of clustering, whereas the decline beyond 5 clusters suggests that too many clusters can be detrimental, potentially due to each cluster becoming too small and specific. The k-modes algorithm outperforms other clustering algorithms, including k-means, k-means++, and k-harmonic means, in terms of MRR and F1 score. Principal component analysis, PCA, was employed to reduce the dimensionality of POI vectors and cluster center vectors to 2 dimensions, facilitating a detailed visual analysis. This analysis revealed that some data points significantly deviate from the central region, identified as noise points. Notably, K-modes and mini-batch K-means algorithms effectively recognize and disregard these noise points, assigning them to the nearest cluster and minimizing their adverse impact on clustering outcomes. In contrast, algorithms like K-means, K-means++, and K-harmonic means incorrectly identify noise points as cluster centers, which is suboptimal. The K-modes algorithms' cluster centers are evenly distributed in denser data regions, whereas mini-batch K-means cluster centers are located in sparser areas of the data. This indicates that the K-modes algorithm is more rational and effective in selecting cluster centers, ensuring they are located in the true core areas of the data and enhancing clustering accuracy. The study demonstrates the Appformer approach as a novel method for predicting mobile app usage, leveraging innovative multimodal data fusion, feature extraction strategies, and a transformer-like architecture. Appformer outperforms existing methods on several predictive performance metrics, such as MRR and F1 score, showcasing its robustness and efficiency in predicting mobile app usage. However, the study also acknowledges limitations, including challenges in data fusion, feature extraction, and model updates and maintenance. These limitations highlight the need for future research to improve the Appformer approach's applicability, performance, and adaptability in the dynamic field of app usage prediction. I apologize, but it seems like there is no content provided to refine. Please provide the original transcript, and I'll be happy to help you refine it according to the guidelines. I'll transform the text into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth, and highlighting novel ideas, significant findings, and important arguments presented in the original text. Deep learning techniques have emerged as a promising approach for predicting smartphone app usage based on various user behaviors and environmental factors. A comprehensive review of existing studies reveals that traditional machine learning models, such as K-means clustering and support vector machines, are limited in capturing complex patterns and relationships within app usage data. To address this limitation, multitask learning is introduced, enabling the simultaneous learning of multiple related tasks, which share knowledge across tasks to improve overall performance. This approach is particularly useful when dealing with large datasets and complex tasks. App usage prediction requires considering both short-term and long-term dependencies in user behavior. Recurrent neural networks, RNNs, specifically long short-term memory, LSTM, and gated recurrent units, GRU, have been successfully applied to model the sequential nature of app usage data. These architectures are well suited for capturing temporal dependencies and have been widely used in natural language processing tasks. Transformers, a type of neural network, have also been explored for app usage prediction. By treating each app as a unique token in a sequence, transformers can learn patterns and relationships between apps over time, capturing long-range dependencies. Incorporating external factors such as location, time of day, and weather conditions into the prediction model significantly influences app usage patterns, improving the accuracy of predictions. Future directions for research include integrating additional data sources, such as sensor data from wearable devices, and developing more advanced deep learning models capable of handling large-scale datasets and complex tasks. This review provides a thorough overview of the current state-of-the-art in smartphone app usage prediction using deep learning techniques, highlighting the potential for further advancements in this field.